Is the recording started? No. Okay, good. Fine. So today we will discuss about a particular topic that is how do you evaluate the hypothesis? This would be interesting because you are also doing your assignments and you are doing the performance analysis of the algorithms that you have implemented, of the classifier that you have implemented. Particularly, you are working on decision tree. So when you make a performance analysis, you are measuring, for example, the as we have discussed, that error of the classification. So we know that there are two types of errors that we consider when we design the classifier. Actually, there are three types. When you design the classifier, then on the training set, you check the performance, how good is the classification as far as the training samples are concerned by checking the training error. And then you can check whether your model has become generalized by checking your performance on the test dataset, which will give you the test error or generalization error. But in between also, sometimes before going for checking for test error, the training dataset itself is divided into two parts. One is training set, another one is validation set. And you can you can develop the model on using only the data from that part of the training set which is meant for training, and then you check also the error on the validation set. So in this way, during training itself, you have an idea that how good could be your generalization error, what could be a generalization error. Then you actually test over the test data set to report the generalization error. So these are certain strategies or certain approaches are there. But today I will discuss that when you are measuring this performance, how sound is that measure? Say you are basically measuring on a particular instance of examples, be it a set of training examples or be it set of test examples, because test set is also is a kind of level data, which you have specially you have just kept it aside for checking the performance. So when you are doing some estimates, it's a kind of point estimate of that combinations. But how far this estimate will be true if I change the data set? So how far it is data dependent? So that is one of the questions that we need to consider when you are judging the or evaluating the performance of any particular hypothesis or classifier. So in our jargon, will be using still the word hypothesis, what we have used in the concept learning topic. So this is the chapter. You should read this chapter about on this topic. So this is what I was discussing, that our objective is to estimate the accuracy of a hypothesis for the performance analysis of that particular hypothesis. Now, when you have a very large data set, we have already discussed that your results are more stable. That means the kind of accuracy you are getting, that would reflect the general trend, because your data is also very large. But if you have limited data, because large data set you may not be having in most cases, right? But you may have also. Now today's world, there are a lot of data sets, but that is also another issue, that how do you work with large data set. But I'm not discussing that part. Let us consider that your data at your hand, and there are it is limited in the sense that you are not sure whether it has captured the variances, what is present in the domain in your data set. So that is, in that way, when you have a small data set, you have always at the risk of missing some of the characteristics in your model to reflect in your model characteristics of the domain from where you're getting your data, the process which is generating the data. So naturally, when though you make a model good for training examples, in the test examples, the model will not give that kind of performance. We call that, in fact, that kind of situation is also overfitting. Now, but no, it may happen that you will always come up with certain kind of hypothesis because of the limitation of data. That problem will still remain there. So, so there are two kinds of things what we check. One is a bias in the estimate. So biased by this data itself, and the variance in the estimate. That since you have a limited data, so or estimates could vary to a great extent. It's not clear. Is there anyone? Yeah. So as I was mentioning, that when you have a bias, may not be the same on unseen data, and more problematic in a rich hypothesis space, because rich means a lot of I mean, the hypothesis space is large, and also you have many options. So, which true hypothesis, which one is the true hypothesis? That itself is difficult to find out in that case. So, and of course, you have to estimate using test data only in that case. Any kind of performance you are doing, finally, it is not the performance on training data that you would be reporting. You would be reporting performance on the test data in this regard. And variance, as I mentioned, it may vary with the test data set. So if the size is smaller, then greater is the expected variance. So that is what is considered. Now, let me just give you a very brief overview of this expectation and variance. Now, we have already gone through the courses on statistics and probability, the fundamentals of concepts in these areas, and you know what is expectation, what is variance. Just for the sake of completeness, I'm just mentioning it. So as you see that if I consider any particular random variable which can assume some value in a particular domain, so we are considering here a domain is either a discrete set of values or a finite domain, or it could be a continuous domain. So anyway, so this is how the variance is, expectation is computed. Of course, x is considered as a numerical value. So x is not the categorical value in this definition. So you get the expectation of x as you understand that it is defined in this way. That it is basically the average of the values of the random variable when the weighted average, when the weights are proportional to the probability of that particular value. So for an empirically, one of the measure could be, since it is average, you can simply consider the samples which are randomly drawn for that random variable, and then you can simply take the mean of that sample as an estimate of this expectation. And in a continuous case, it is a probability density function that defines the probability distribution over the space. So you need to do integrations. So these definitions are quite standard. Similarly, the variance of a random variable, it is the expectation of this square of deviations of the variable from its expected value. So which is actually also the definitions of variance of any particular data set in a one dimension. So this is the kind of computations involved in estimating them directly. If I give you the random variables value, you can do that. Now there are two questions that we will be addressing in this particular issue, that when we are evaluating a hypothesis, what is the best estimate of the measure that you are using, best estimate of the accuracy of the hypothesis when you are in examples are randomly drawn from a distribution. And probable error in the estimate of accuracy, in the sense that first you can say that what is the range. So the value what you are getting, that's a kind of point estimate, but what would be the interval on which most probably these values will lie. So can you get that probable range of estimates so that you can say that for example your true estimate lies within it with high probability of confidence, say 95%. So if I do experimentations, if I randomly draw test samples from these distributions and of course consider they are leveled and they are true levels, and then you can estimate the accuracy. So what is the range on which most likely these accuracies, the values would lie, and with probability say 95%. So these are the things we'll be considering while evaluating the hypothesis and while checking the performance of a particular hypothesis. So this analysis, just we'll be presenting a very brief outline of this analysis. Let us consider you represent instance by an X. That means it's a training example, for example, an element of the training data set. We have used this notation consistently, say with ordinary D and the curly D for distribution. And S is a data sample which is of size say n. So S is the set of data sets of size n, and H is a hypothesis again in the form of this Boolean function, right? So you are mapping your examples, training instances to either 0 or 1, like two classes. So target function, there is a target function, and your hypothesis is a prediction on the target function, right? So what you are trying to do, you are measuring the error of your hypothesis in the sense that in how many samples they do not agree. So this is one simple definition. So if I consider the X is the here decision from the hypothesis H, and Y is the decision from the target function F. Then when they do not agree, then we basically count it. So we can write in the functional form in this way. I hope now it is more clear. As you can see that it is basically if fx and hx do not match, then the value of function small e in the notation, it would be basically 1. So you are counting how many times it has occurred. And if you consider the total number of examples, and what is the fraction of examples where they do not agree, that is what is the sample error. And or you can consider here training error if S is the training sample only. Whereas true error is your this. Now S could be test sample also, because sample error is if S is test, because we will be checking on test samples as I mentioned. So consider S is any sample of instances whose labels are known to you. So say in this case it's a test data set on which we will be discussing. So this is the estimate. SH is the estimate of true error, EDH. You can see that EDH in this case, that is italicized D is that domain, whole domain. It is basically representing the population. So in that population, how many instances are not agreeing with the target function when you consider the hypothesis? Okay, that is true error. Now, if I consider that there are R errors in n samples, so according to our definition, I can write it as R by n, right? So that is the fraction I was mentioning, and that is your sample error, or that is your estimated error of the true error. Now, when you are trying to do this kind of analysis, now we follow certain model probability distribution. So this process can be modeled as Bernoulli distribution. So you may consider that, say in this distribution, what is the Bernoulli process? It is basically provides an outcome with either with a certain probability for success and of course the complementary probability for the failure. So we denote it by 1 and 0. So in this context, your error, if the error occurs, then the random variable which represents this process, which the outcome which represents the outcome. So value of the random variable will be 1, else 0. So here the success and failure, the term is little fuzzy. So actually, if you get an erroneous sample, that is the success for this process. So anyway, so you consider this, and let us consider that the underlying probability, that is the model, statistical model, that probability that it would happen, it would be erroneous or x equal to 1, that is p. Okay, so what should be the probability of x equal to 0? That is 1 minus p. Fine. So what is the expectation in this case? Can any one of you tell me what should be the expectation of x when x is a random variable?
P.
Right. So expectation of x is p, because you see that how do you compute it? How do you come to that conclusion?
Sir, 1 into p, 0 into 1 minus p.
Exactly. I hope it is clear, no? Others, it is very simple. Already you know these things. So this is expectation. And what should be the variance?
P square minus P.
Pardon?
P into 1 minus P.
Yeah, P into 1 minus P. So again, this variance computation, expectation of x square minus x square of expectation of x. That's the simplification of the expression of variance. If you do that, you will find this. Now, this is the process. This is a variance. So you can see that in this model, at least you can get some estimate of the variance. So how do you get the intervals that will be coming? Will be coming also. So let us consider also once again. Let us see that how do you define the bias and variance probabilistically with respect to this kind of. If you consider it's a random variable, as you see that in this case, your probability of error for a sample we consider p. So p is your, I should say, the parameter which you have estimated for the. See, in the Bernoulli distribution, Bernoulli process, the probability distribution has the parameter p, as you understand that. That is the parameter. Now, probability of r errors in n samples, that would be following this kind of that would be the probability. Which distribution it is following?
The binomial.
It is following the binomial distribution. Okay. So if you have n draws, and out of which r draws will be event, there will be the event will occur r times. So you would probably say every event is occurring with probability p. So you know that the exactly r times if the event occurs. So this is the probability that exactly r times the event will occur out of n trials, and that is what is your for n samples. So so what is the expectation of that number of errors in n samples? What is the expectation of number of errors of n samples? So in the binomial distribution, if you consider the expectation of the random variable, now these are the random variables. Okay, so you know that if you do the maths, you will get these values. Huh? if you apply the respective expressions. So the expectation of the number of times the error occurs out of n trials should be n into p. It is the same. You can see the fraction of number of samples. That is the number. And variance is n into p into 1 minus p. And so expectation of the r by n itself, that is the estimate. The estimate is r by n. Now we find actually that is also the true value p, what is used as a parameter, right? So your expectation of your estimate is also the true value here, and we'll see that it means that there is no bias. So if it is not, then there is a bias. That means your true estimate, true value of your parameter is something, and your expectation of your estimate is something, and that is what you are estimating, that parameter itself. Then the difference will be the bias.
So what is R by N, sir? What is R by
R
N?
by?
What is R by N, sir?
Yeah, R is already defined. Na? You can see it is defined. What is R? Number of times you find
Error has occurred.
a sample is erroneous. That means the hypothesis and target function, they do not agree. It is not, the levels are erroneous, okay? Your predicted levels are erroneous.
Sir, here
N is this. That is the size of your data set on which you are testing.
Sir, what does E R by N signify, sir?
E is expectation.
Yes, sir.
I was mentioning, na? E is expectation. So in the previous slide, actually, I have actually there is a bit, yeah, I understand bit confusion because I have used the same functional notations. So here E is expectation. Okay, this is yeah. So this is error. Yeah, that's why the ambiguity. So you may note this. This is actually representing the error. Okay, estimate of the error, and this is our expectation. So this bit of ambiguity is there. Okay, so in my discussion, this is expectation. Is it clear now? Is there any question?
How we are calculating variance P at last line? I cannot understand.
Yeah. So variance you can calculate. Actually, you can calculate the that you can calculate the variance of R, where R is a random variable for the binomial distribution. If you compute, that you can do it using straightforward expressions. So you know that what is the value, what is the range of R? What are the values R can take?
So 1 to N, anything.
0 to N. R can be, there may not be any error also. So R is 0 in that case. So R varies from 0 to N, and for each value of R, this is the probability. So using this, you can compute the variance, use that expression, expectation of square of deviations from its expectation of the random variable, and in a way you can compute what is expectation of x square, okay, and then what is expectation of x. Already you have computed that. So expectation of x will be this. In this case, now you consider all x is representing this symbol R. So you have to find out these two things, and then you know that variance would be the difference of expression of x square and expectation of x whole square. And that value would be this. If you do this computations, you will get this. So I will advise you, please read the basic statistics book on basic probability and statistics. So all these discussions are there. So that is what is your variance for R. Now there is once again there is a mathematical relationships that if any variable, random variable, if you the variance of a particular random variable, if you consider scaling factor, the scale, it would be scaled by the square of that scale. If the variable is scaled by a factor, say k, the variance would be effectively scaled by its square. So in this case, this is scaled by 1 by n, so it would be scaled by 1 by n square. Is it clear?
Yes, sir.
Okay, so so this is how you get the variance of the estimate, and so you get this is the variance of estimate as I mentioned. So for I mentioned already that this estimate is unbiased because no, you have this thing. So the bias of the estimate, as I was mentioning, is the expectation of estimate minus true parameter value. So in this case, unbiased because both are same. Your true parameter value is p, and your expectation of your estimate is also p. Expectation of r by n, that is your estimate, that is also p. So in that case, there is no bias in your estimation, but you have a variance, and that variance is you have this p into 1 minus p by n, and you can use r by n for that. You should also just note the difference. The term bias could be used in various contexts. Like earlier, I have used the term bias for inductive bias. Now that is something different. It is a set of assertions on which you have assumed, on which your logical or arguments are placed. But whereas bias of estimate, in this case, it's a numerical quantity, as you can see. So what is the probable range of estimate? So we have variance, but how the variance can give you a kind of range with certain probability? Now there, you have to use once again the probability distributions, the modeling of the probability distributions with respect to your estimates. Now, one of the interesting thing is that if you, I will also discuss in subsequent lectures. So let me just give you the results. So we'll be discussing that. So you see that your estimate of the error here, it is estimate of the error is r by n, and if you given no other information, what is the most probable error in the distribution, given the distribution, that means true error. Now you can consider that since it is unbiased, so most probable would be this. So that means if you get a probability distribution of this estimate, what is the most probable? This is the most probable error. But what approximately 95% probability, actually this is the use of the variance. I'll be discussing that. You see that this is a result I am just showing you, but there is an theoretical analysis behind this result. But let us first understand the result, then we'll go for a bit of theory later on. So the result is that you see that this is giving your interval. That means you can, once you have estimated this, that itself is defining the most probable estimate and also the interval. Is it clear? So this is how the interval is given. I mean, I'm talking about from the interpretation of these particular computations or expressions. Then I will go further. So we call it actually confidence interval for 95% probability. So there is some reason why it should be working for greater than equal 5s, and minimum should be 30 when ESH is fine. These are certain results. So smaller estimate value requires larger sample size. This is a region that if you want to have your errors, if your errors are getting smaller, then for this variability, you should have the larger sample size. Now, example, let us consider an example. Say you have a training data set, or sorry, test data set, and it's basically a data set on which you will be checking your hypothesis. So let us consider a sample set in that case. So you have a sample set of size 40, and out of which 12 are erroneous. Erroneous means their prediction is wrong with respect to your levels. So your error would be r by n, fraction of erroneous level will be, estimate of your error is r by n, which is 0.3, and then your confidence interval using the formula would be this, and which means that finally you will get an interval. So with the result 0.3, that's a point result. But we should not be interested on point result. We'd be more concerned that what could have been the variability. So you see that it could be as low as 0.16, again as high as 0.44. So that is the kind of with 95% probability. If I consider with 97.5% probability, it is less than 0.44. Actually, there is a distribution, and if you plot this distribution, the curve would look like this. You know, many of you, it is kind of a normal distribution, looks like a normal distribution. Actually, binomial distribution in discrete variables also. When n is sufficiently large, it looks like, and that is why the restriction of n number of samples is there. So these are the case. So from the properties of binomial, and which is, as I mentioned, which becomes normal for a large n. So confidence interval is that interval containing the true value with probability n%. That is the definition of n% confidence interval. So previously, you have computed the interval 95% confidence interval. So that is how we interpret it. And for large sample, binomial distribution approximate normal distribution, as I mentioned. So if I study the normal distribution, then you know that in the normal distribution, there is a very predefined, when you normalize it, you can tabulate the corresponding probabilities, probability of certain intervals. So you can tabulate them. Like if I consider, for example, this is the way an interval is defined. That means in a normal distribution, you have these two parameters. One is, this is the expectation of the distribution, or which we call the, in usual term, which we call as mean of the population, right, on which the distribution, you are observing the distribution. And sigma is the standard deviation. Here is the parameter. So sigma provides you the kind of spread you have. Now you consider with this distribution mu and sigma. So if you define an interval, say mu, this, what is this value? This is mu plus Zn sigma, and this is mu minus Zn sigma. So that is the interval. And what is the probability if a random variable follows this distribution? Probability would be area of this curve under this interval. Now, this is actually, depending upon the value of Zn, centering on mu, this is already predefined. Already you can tabulate it. I mean, that is the interval I told you. So you see that depending upon the your confidence interval, if it is 50% confidence interval, so the value of mu is 0.67. So naturally, your interval, you are narrowing down your interval, but then probability of your estimate would be within that interval would be less, right? 0.57 only. So, but when you are expanding your interval, so you see a particular value here, which you have used earlier, for 95% confidence interval, there is, we call it, say, let us call it the value of Zn as a scale or whatever, the Zn value. So Z value. So this value is 1.96. So if I put this value as 1.96 and compute the interval, I can say that would give me the ranges on which my estimate would lie with probability 0.95. So if I just go back to my that result, then you appreciate it, this particular analysis. See, you see that here I have used this factor here, right? This is the thing here. Now this is actually representing that sigma, or the sigma or standard deviation of that particular distribution, which is likely, which is almost like Gaussian. So if I consider, it is approximating, it is what it is doing. It is modeling the error, probability distribution of that error as a Gaussian distribution with, say, mu and sigma, where mu value is this and your sigma is this. Now, why it is so, I will also discuss just a few minutes. Just let us see that why it is so also. Right? So let us proceed. So what should be a general approach for deriving this confidence interval of an estimate? So let us consider that, and then that would give us the answer in this way. So let us consider that y be the estimator of a parameter p. So y is the random variable, which is the estimator of a. See, y the random variable is its estimator itself. The random variable, like r by n. No, that is your computation. Now, that is actually the random variable, because depending upon the value of r, the value will change, and r has certain probability distribution. Anyway, so if I consider y is the estimator of a parameter p, and so you can determine always the probability distribution of y. So it's the same, like that it means that in our context, if I consider an estimator like r by n, right? R by n was our estimator of parameter p. We have considered, say, estimator of p is r by n, for example. What is p? P is that probability of a sample is error. That is the Bernoulli process I told you. Now, actually, if I consider n trials, then it becomes a binomial distribution I have already mentioned. So the distribution, probability distribution of y is actually binomial distribution. So if it is a binomial distribution, then we know that expectation of r, already we have mentioned all those things, should be n into p, and variance of r would be n into p into 1 minus p. Is it clear? So this probability distribution in our context is binomial distribution with mean or expectation is, once again, expectation is n into p, and variance is n into p into 1 minus p. We have discussed in the previous 1 minus p. Okay, if you remember that, these things will be clear. Now, naturally, if I consider r by n is my estimate of that parameter, I can use also them for estimating the variance. Okay, again, there are issues that how sound is, what is the range of estimate, etc. That I'm not going to discuss everything here. So now our objective is to determine the n% confidence interval, and by finding the thresholds of that. So I told you binomial distribution follows normal distribution. So that has connotations here. So you can also consider as if they are normal distribution with those mean and standard deviations. So there is a theorem called central limit theorem. Many of you know that already, and you can also just consult the book of probability. So this theorem is very interesting and very powerful theorem, and it can be applied in a very generic situation because of this. So what it says that if you consider the estimation of mean of a distribution, so whatever may be the distribution of a particular random variable, but for the mean of that distribution, if you are going to estimate, then that would follow a normal distribution. That is very interesting, and it's kind of a that can be, and since it follow a normal distribution with, that's the central limit theorem. So if you have more number of samples, then it would be more tending towards becoming an ideal normal distribution, and with certain variance and mean. Now, the mean of the distribution, normal distribution, would be the same mean itself, which you are estimating, but the variance would be basically, it would be divided by the number of samples. So this is what is, that means variance of the distribution. If the variance of the original distribution, for example, you are estimating mean of a distribution like dy. So what is the mean of a distribution? Mean of a distribution So dy has a, let us consider dy has a mean, say my, and say a variance, let me write it as sigma square. Let us consider this distribution has this. Now, when you are estimating the my itself, then actually it follows. Now, this distribution, probability distribution could be, of any other form. It need not be normal. But when you are considering the distribution of its mean for that estimation, now that itself would be a normal distribution. That would be normal distribution whose mean would be once again the same. When our expectation would be the same, that means mean of that estimate itself, but the variance would be reduced by the scale factor of the normal number of samples, right? So actually you are reducing the variability of that estimate. So that is interesting. Now this is used in our expression when we have considered the confidence interval. So this is I will be again explaining. So in the same way as I mentioned, as you can see that consider any random variable of some distribution and which characterized by its mean and standard deviation sigma, which is defined here. Now you draw an independent observation of y, right? And then you consider the average. Now that is the estimate of your mu here, estimate of the mean of the distribution. So this average, following the central limit theorem, this average will be ideally following this kind of distributions. It's a Gaussian distribution or normal distribution. Right. Okay. So there, right. So with this, just now, if I go back and then now we can understand the expressions what I have given here. So I'm talking about this. So you see that what was the if I consider the binomial distribution of the random variable ESH, this was the expectation and this was the variance, right? So when you are estimating the mean of that binomial distribution itself, so then again you see that the mean of the parameter itself, then you see that rather mean of the distribution, P is the mean of the distribution itself here at the end. So when you are estimating it, then it becomes, you see that this is what your the corresponding expectation, and you are dividing the variance by n, right? So that is your Gaussian distribution. So that is how actually you got these expressions, and just I have provided these expressions before explaining why it is so. So I hope you will be able to follow the analysis. So now let us come to this last part of this discussion, that how do you compare two hypotheses? Now this should be interesting. One is that when you evaluate a single hypothesis, you can find out its performance, and then you can say what is the range of accuracy or error with certain percentage of confidence interval or certain percentage of probability. Now suppose I give you two different models or two hypotheses. Now I would like to see that which model is better. That also should be from the probabilistic point of view interpretations. Which means that if I consider just the point value, that means you just consider a typical data set on which you run H1, on which you run H2, find out their errors, and suppose some error is greater than the other one, you should not say that this is better than the other one. Now that is the common mistake we do many times in our research, right? You have to statistically you have to say whether it will be most likely it will be better. Most probably, in most cases it will be better, or most cases it will be it will be worse, or they are equivalent. I mean, not much of distinction. Sometimes H1 will be better, sometimes H2 will be better. So this is the way you should compare when you are comparing a model. So once again, no, from this kind of statistical theory or probabilistic interpretations, you can do that. Now here, what is your random variable then? So random variable itself is the difference of this performance. That is your random variable. So now you should find out that in what interval this D value would lie. So intuitively, you can see that most likely if they are comparable, the D value would be most likely 0, right? No difference. So with high probability, most likely they will be 0 or around 0. And then if one of them is better, then actually suppose if H1 is better, D would be positive. No, sorry, it is error I am talking about. So D would be at the negative side. So you will find with high probability D would lie at the negative side. And when say H2 is better, then actually D would be positive with high probability D. So by looking at the distributions, by computing the variability of D itself and its expected value, like the same way, the statistics I told you, you can find out the confidence interval over which the D would lie, and from there you can take a decision which one is better. That is the kind of approach. No, you can see that exactly that is what we are doing. Actually, the variance could be computed by drawing from both, because we are assuming both the processes are independent and they are following normal distribution. So variance would be computed of this variable, the variance would be computed in this way. And then you apply the same technique of finding out confidence interval, and from there to decide which one is better. So I just figuratively, I've just shown you, if something is, for example, if your D prime, if you find it is lying in this range, then you say that no, one of them would be better. Like in this case, say H1 would be better. I mean, of course, I have written greater. So in that case, naturally, ES to H2 is better. Right. So this is also you can apply. When, because you are using this kind of statistical test, why not you apply in pruning? Because as you see that when you prune, you get a different model. When you prune a decision tree, you get a different model, and you get two different. In the algorithm of pruning, it says that unless it improves, it stops improving. Now that improvement is in question is itself a little questionable, isn't it? So you are just looking at that instance only. How do you know it would be good for other instances? So that is the question. So ideally, what you should carry out this kind of test. Of course, it will be computationally expensive, but no, you can improve your results, or you can improve your decision making process. So I hope this is simply the repetition of my discussions. So just a summary, you can see in a way that the difference itself is your estimate. So you can observe how many times it has occurred. I mean, you can observe number of times these differences with different data set, portion of data sets, and then you estimate average and your variance. You know that there is also a theory of estimating unbiased variance, just dividing by 1 by k minus 1. I'm not going into those details. And then the confidence interval can be denoted in this way. Instead of Z, we are using T because we model it in terms of T distributions. So it's nearly as N is large, it will be following normal distribution. Right. So that is what is another thing. We talked about also k-fold cross-validation earlier, I hope. So when you are doing this generalized checking the test error, sometimes with limited data, it is difficult for you to have an exclusive test set and exclusive, say, training and validation set, for example. So instead of what we do, we consider the whole training set. One is for training and another one is for validation, but we rotate it. That means, no, you can there are different ways you can do. Normally, one popular way is that you make k partitions of your training examples, and keep one partition for validation, other k-1 for your designing or developing the model. So perform the test and check the error. And you just know, exchange, you make, alternately, you make one of these partition as your validation set. So you will get k results. So you will get k instances of your results. Now you can apply all these statistics. So that is what is the part. So when you have k-fold cross validation, particularly, you should not give any particular point result. Rather, you should give result of this distribution. So so that is the summary. You can say that you should, when you do performance analysis, it should have a probabilistic interpretation. Otherwise, it should not be accepted. It's not statistically accepted. It's a kind of chance result that you are reporting, and that is flawed. So just to summarize of this particular thing, that as we mentioned that in this case, our error estimate is unbiased because of this theory, and we can also compute its variance using this by modeling it as a Bernoulli process. And we can also compute the n% confidence interval, and also we can evaluate competing hypotheses, again using the similar probabilistic analysis. The use of central limit theorem you should note for estimating particularly average of any statistics. Then you can model it as a normal distribution when your sample is of course large, and from there you can get the confidence interval. And in k-fold cross validation also we can extend this particular technique. So with this we can conclude this particular topic. And as I mentioned, as you know, all of you know, that tomorrow you will have your first quiz, and the quiz will start at 12. So please join. Maybe you can join a few minutes before that. And when the quiz starts at 12, and then the quiz will end at 1. And please maintain your honesty and integrity while appearing for this particular quiz. So that is nevertheless I never to mention, but not just to remember. So let me take your attendance first.
Sir, there is a small request. Sir, as we have a test for IR from 11 to 12, so can you delay a bit, just like 10 or 5 minutes? Like you can start from 12, 10.
So 5 minutes. Let us have 5 minutes then. I will.
Yes.
Or 10 minutes. What do you want? Because then in that case it will be 1:10.
Yeah. Yes, sir.
So I think in that case, please join, and I will then. Is Joyশ্ree here, or who is here as a TA?
Yes, sir. This is Anunay.
Anunay,
Yes,
huh?
sir.
Anunay, yeah. So and Ankita is also here. So Ankita, I will also inform, but please note it down. So tomorrow, you can also please write it on the MS Team page. The test will start at 12:10, right? And it will be over by 1:10. Okay.
Thank you, sir.
Okay. Okay.
Sir, what is the pattern of
Any other question? Any other
The
question?
syllabus would be concept learning and decision tree, no, sir?
Yeah. Syllabus will be concept learning and decision tree. Not this one.
pattern of test, short
Okay, sir.
test or long test?
I'm not getting the question.
Sir,
What
what
type
is
of
the
question we
pattern
have,
of
that
test?
MCQ or
Sir, this is
descriptive?
descriptive or
It
MCQ?
would be MCQ, MSQ, and numerical. There will not be any long questions. Huh?
It's a platform, sir.
Pardon?
It's a platform.
For the exam.
Platform is Moodle.
Okay, sir.
So, sir, we have to write and scan and then upload, or?
No. It would be interactive. I mean, the Moodle, there will be a link for quiz. If you click that link, you will get the questions. You have to answer there itself. You will get all the options. You have to answer online. It's an online test. Any doubt? Any further doubt?
computational complexity.
Your voice is very faint.
Am I audible?
Can you tell me once again?
Yes, sir. Sir, is packed there in the syllabus? Computational complexity, which is included in the slide.
I'm not getting your voice actually. Can anyone just repeat her question?
She says that there is a pack in our syllabus, pack model and complexity theory.
There is a gap on.
Sir, pack model.
PAC model.
That
PAC
is in
model.
chapter 7, I think.
Yeah, it is there now. Whatever has been covered in my lecture class, it will be there. I mean, you should know in the book. You should read those concepts. You are talking about PAC learning. But no, it is just the concept itself. I mean, don't go into details, but the definitions that should be. So you follow also the lecture slide and the corresponding topic in the textbook.
Sir, in the previous exams, like in the AI, we have given in the model, but sometimes we're getting autosave failed and timeout because of load. So
no, actually, it
do
should not
in that
happen.
case?
It does not happen in our case because we will be using CSE. This CSE module server, it is not loaded that much. Okay.
Okay, sir. Okay.
I have not experienced this. That happens. I understand on the institute's module server. So that is one reason we are using our departmental module server. Oh no, there won't be any technical glitch. If there is any technical glitch, no, we need to consider that. I understand that, but no, try to I mean, do your best and try to be cooperative while attending this test. Otherwise, no, this evaluation will be very difficult for us to carry out. Okay, so all the best for you. And Ankita, can you just write a few things on the MS team? One thing is that the test will start tomorrow at 12:10. Secondly, the test will be online on Moodle platform, CSE Moodle platform, right?
Okay.
These two. I think these two will be sufficient. Others, though, I have already mentioned.
Okay, sir.
Okay. Okay, thanks. Bye.
Thank you, sir.